In this video, I want to talk about predicate logic semantics with variable assignments. Essentially, the way to kind of talk about this video is to prompt it with some earlier information. So you want to recall that in predicate logic, we make use of a valuation rule. And all that valuation rule is an assignment up to well-formed formulas of a value of true or false in classical logic. So let's let alpha or A, you can just read it as A, just be a series of names. And these names aren't necessarily distinct. They're just a bunch of names. We'll let the uppercase P be any n-place predicate, and phi and psi are well-formed formulas in the language of predicate logic. And these can be any formulas if you want. If looking at these symbols is confusing, you can just kind of substitute whatever well-formed formula you want. Given that these are some symbols that we'll make use of here, we can define a valuation function, which again is an assignment of truth values to the well-formed formulas. So if we have P followed by a number of names, that is, if P is an n-place predicate and it's followed by n names, and this is a closed atomic well-formed formula, that is, it's a formula without any free variables, it just is followed by names, then we can say that this particular formula, this closed atomic formula, is true relative to the model that we're talking about, if and only if the interpretation of the names, that is the objects they refer to in the domain, is found in the interpretation of the predicate, or what's sometimes called the extension of the predicate. And if the names are found in the interpretation of P, then it's true. Otherwise, the particular formula will be false. So really simply, if we have a name like Al is a person, this is going to be true if and only if Al is included, the object Al is included in the class of persons. The rest of these are pretty standard from propositional logic, so I won't go through them. But the other one I want to draw attention to are 6 and 7 here. One presentation of predicate logic involves the unpacking or the evaluation of quantified well-formed formulas in terms of unquantified formulas that make use of names. So we have here at line 6 that a universally quantified formula is true if and only if we can uniformly substitute every x, that is every variable that's found in the formula here, with a name A or alpha, and it comes out as true for every name A. So the idea here is that, let's say all men are mortal, if and only if we can go through each one of the items, MA, that is Al is immortal, MB, Bob is immortal, MC, that is we run through all the names in our language, and all of those sentences come out as true. With respect to existentially quantified formulas, like at line 7, we say that EX phi is true if and only if phi, where we substitute a name alpha for X for at least one name. So someone is a mortal if and only if we can take the variable that's found in the EX MX and replace it with some name, at least one name. Let's say L, and L is Liz. So provided Liz is immortal, at least one name, this formula comes out as true. So as long as we can have a simple unquantified sentence like Liz is immortal is true, then someone is immortal. So the two things I want to point to and that motivate this video are the valuation rule with respect to the first one. That is, the valuation rule is defined for closed atomic well-formed formulas, that is formulas without free variables, that is formulas that involve names. And then also the use of names to unpack the truth conditions of quantified formulas at lines 6 and 7 there. Now, a case can be made that there is a problem with unpacking the truth or defining the valuation function in this way. The first is, again, note that the valuation function is defined only for closed well-formed formulas. This means that it's undefined for open well-formed formulas, formulas with free variables. So a formula like Px, the valuation function doesn't take it as an input. It just doesn't yield a truth value as true or false. And we might say this is problematic, or make a case for it being problematic, and saying that we want a more inclusive evaluation function that does assign truth values to these types of formulas for a couple of reasons. The first is that there might be some formulas that we want to assign truth values for, and those formulas have free variables in them. So let's take the two-place predicate I and XX, where I is the identity predicate. We might say that if we have this relational predicate I and followed by the appropriate number of variables, we can assign a truth value to this because it doesn't matter which object that we substitute for x, this formula will be true, and so IXX will be true. But this isn't really allowed in the original valuation function because it only defines the truth value for closed atomic well-formed formulas. A second concern is the compositional concern. The compositional concern is that we would like our semantics to be determined by the parts of the formulas. That is, we want the whole formula to be determined by the parts. And so if we take a look at the existential quantifier here, we might say, well, the existential quantified formula has two parts. It has the existential quantifier and the px part. That's one way of thinking about it. So there's the existential quantifier as one part and px. And we would like it to be determined by px and the existential quantifier. That is, the whole formula, this whole formula here, is determined by its two parts. Rather than saying a formula like this is true provided we do some operation on it, or it's true provided this disjunction of PA or PB or all the way to P, some name is true. That is, one name is true. So that's at least a desire. It's not necessarily a problem, but it's something we would maybe like from our logical system. A final concern is that we'd like a tighter relationship between the syntax, the grammar of the logic, and its semantics. That is, the system that defines its meaning or assigns it truth values. In some systems, it is actually defined, the open well-formed formulas are defined as syntactically well-formed formulas, but they're not interpreted. And so one desire might be that we'd like any well-formed formula to have an interpretation. Any grammatical construction you can make also has meaning to it. And so we'd like a more inclusive valuation function that assigns truth values to these open well-formed formulas. A second issue is that the valuation function assumes that there is a name for every item in the domain. And we might take this to be controversial. So one thing to note is that when we specify the truth value of existentially and universally quantified well-formed formulas in terms of these non-quantified well-formed formulas, we're assuming that every item that we're talking about is named. So we say that for all x, phi is true, provided we can substitute for x a name, and every single one of these sentences is going to come out as true. But the issue is not here that we don't have enough names to name all the objects that we want. The issue is that there's no guarantee that every object in the domain is named. So if we say everyone is a cat, or everyone is a person, or everyone is happy, what we're saying is that this sentence is true provided each and every item we can name is true. But what if there are certain happy things or unhappy things or certain people or cats that aren't named? And in which case our generalization is only over named things rather than the objects themselves. This point is worth kind of dwelling on just a slight bit longer. Another way of putting this is, let's say we wanted to make a claim about all cats. And we wanted to say that all cats are curious. Well, in terms of our current valuation function, we would say that all cats are curious is true if and only if for every cat that we can name, that cat is also curious. But this seems problematic because we might say that there are some cats, for example, stray cats, that are unnamed, and we want our generalization, our claim that all cats are curious, to apply to them as well. In order to ensure this, we have to make an assumption, and that assumption is that these cats have names, which is a kind of problematic assumption to make. So how do we fix this issue? Well, the key idea behind fixing both of these problems is to treat variables like they're pronouns rather than names. So take the sentence, "it is happy," or we might translate it as HX. The pronoun it here can potentially refer to any item in the domain. Until we fix its referent, we don't know what it refers to. The truth or falsity of "it is happy" is going to depend upon this referent, the referent of X, the variable, or it. Since the referent of pronouns can vary and potentially refer to any object in the universe of discourse or domain, we can use this feature to generalize about objects. That is, we can develop a procedure that allows us to temporarily fix the referent of variables or pronouns. So let's see this a little bit more specifically before we dive deeper into it. Let's take the first problem. The first problem is that we don't have a way of defining the truth value of open well-formed formulas. That is, formulas with free variables. That is, formulas like, px right here. Or he or she or it is a person, to put it in English. But we can assign the truth value of this formula, px, or in English, a sentence like he is a person or she is a person, if we have a way of identifying the referent of the pronoun he or the referent of the variable x. So the truth value of this formula is going to depend upon the referent of the variable or the referent of he. And if he designates something that's not a person, then we can say that px is false. That is, he is a person designates something that's not a person, like a cat. We can say it's false. While if it identifies something that is a person, then px is true. Now, this is the general outline of how we're going to solve this problem, but we'll go more precisely into it in a moment. Let's look at the second problem now. Recall that the second problem is that we take the truth value of quantified formulas and unpack them in terms of unquantified formulas with names. So if we treat variables like pronouns, and pronouns have this capacity to potentially refer to any item, but we just have to fix its referent, we can use this feature or this idea to unpack the truth value of quantified formulas without relying upon names. So here's the general outline, but again, we'll go into the specifics later. So let's take a formula like EXPX, or let's say this is someone is a person. This formula is going to come out as true if and only if there's at least one way of identifying the referent of he, that is the pronoun he, such that the object is a person. The idea here is, let's say someone is a person. We can say that this formula is true provided we take a simpler sentence that's unquantified and make use of pronouns. So we say, let's say she is a person. Now, we don't have a way of identifying the referent of she, but provided there's some way, that is, there's some referent of she in the domain, and this sentence comes out as true, then the quantified formula is true, or the someone is a person is true. In other words, if we have a formula like EXPX, let me write in this little x here, this formula will be true if and only if PX is true for at least one referent of the pronoun, that is the variable x. Similarly, AXPX, or everyone is a person, will be true if and only if on every way of identifying the referent of he or it or she, that object is a person. So just as we did up here, we say that AXPX is true, provided this sentence, she is a person or it is a person, comes out as true for every way of fixing the pronoun in the domain. So no matter what she refers to in the domain, provided no matter what object we substitute for she, that sentence, she is a person, comes out as true, then the universally quantified formula will be true. So in short, AXPX is true if and only if PX is true, no matter how we identify or determine the referent of the variable x. So let's be a little bit more specific in how we solve these problems. And in order to do this, especially in the formal language of predicate logic, we're going to add some additional technical notation or artificial notation. So the first thing we'll do is start with a function or a concept known as a variable assignment. And the idea of a variable assignment, which will indicate as G, so whenever we want to make use of a variable assignment, we'll just indicate it as G. The variable assignment for a model, which a model consists of a domain and an interpretation, this variable assignment G is a type of function that assigns to each variable some item or object in the domain. So the basic idea is pretty simple. The variable assignment takes all of our variables and just takes a variable and says which item it refers to. Let's look at some examples just so this becomes crystal clear. All right, so to illustrate this variable assignment, we're going to introduce a little bit of notation just so it's clear which item in the domain the variable assignment assigns the variable to. So we already mentioned that we're going to use G to stand for a variable assignment. And if we need more variable assignments, if we want to talk about more, we can always use G sub 1, G sub 2, so forth and so on. We could subscript positive integers. But to specify which item corresponds to which variable, we'll make use of G and then parentheses X. So all this says here is that the variable assignment G is going to define or indicate or determine the referent of X. So it's going to specify the variable assignment of X. And we can read G of X saying the variable assignment G takes X as input and it's going to yield an item from the domain as a value. So let's look at some specific examples here. In the first example at the bottom here, we have the variable assignment G takes a variable X and it assigns X, that is the referent of X, is U. So it takes U sub 1 from the domain and assigns it to the variable X. Let's take a look at this same variable assignment, but here it's taking Y as an input and it's going to determine its referent. And it says, well, Y refers to U sub 2. So this is just some item from the domain. More concretely, we might say, okay, here is the same variable assignment G, takes Z as its input and assigns it an item from the domain. And this item is, let's say, a person, and let's say it's Liz. So it's saying that the referent of Z, the object it points to, the object it refers to, is Liz here. And that's all a variable assignment is. It takes all the variables and assigns an item, each variable one and only one item from the domain. So with the notion of a variable assignment in place, we can relativize our valuation function, not merely define formulas as being true or false relative to a model, but we can also define the valuation function relative to a variable assignment. We can indicate this by writing, not when we talk about our valuation function as V sub and then this model sign right here, that is talk about the value of phi relative to the model, but the valuation relative to the model and the variable assignment. So we're determining the truth value. This valuation function is going to consult the model and the variable assignment and then determine the truth value of phi. Just to make this point again, the truth value of formulas won't be determined all on their own, even though there may be some cases where some formulas can be true independent of any model or independent of any variable assignment. But here we're always going to specify this valuation function relative to these two things, the model and the variable assignment. And this is just writing it again. It's not the formula all by itself is true, but relative to these two things, the model and the variable assignment. So this is an important feature, that relativizing the valuation function to these variable assignments in addition to the model allows us to define the valuation function not simply for closed atomic well-formed formulas, but also for open well-formed formulas. And this would fix problem one. And problem one was we didn't have a way of determining the truth value of open well-formed formulas with free variables. And so introducing this variable assignment now allows us to do this. So let's see how this works exactly. Now, one way, and I like this particular presentation, even though it's not the most straightforward, one way of fixing the problem is just to define two different rules for atomic well-formed formulas in predicate logic. So let's let alpha be any name and x be any variable. Now we have two valuation functions. We're adding an additional one. The first one is simply to say that if an n-place predicate followed by n names is a closed atomic well-form formula, then the valuation function takes those formulas relative to the model and the variable assignment and assigns it a value of true if and only if the interpretation of those names, the sort of n tuple, is found in the interpretation of P, that is the n-place predicate or the extension of that predicate. Otherwise, the formula will be false. So this is pretty much the same as before, which is to say that if the objects that are referred to by the names are in the interpretation of the predicate, then the formula will be true. So there's no change to our original formulation of the valuation function for closed atomic well-formed formulas, except for the fact that we kind of make this additional notational difference, but this variable assignment isn't actually impacting the truth value of the formula at all. Where the real change comes about is 1b right here. And 1b says that if we have an n-place predicate followed by n variables, and so this is an open atomic well-formed formula, then the truth value of this formula, that is, the formula will be true if and only relative to the model and the variable assignment, if and only if the variable assignment of each one of those variables, that is the n tuple consisting of the variable assignment, is found in the interpretation of P. Let me put this a little bit more simply. Remember that the variable assignment G takes a variable and assigns it an object or referent. And so if the object is in the extension of the predicate P, then the formula is going to come out as true. If it's not in the extension, then it will come out as false. We'll look at an example of this in a second, but just two kind of quick points to remember. One is that the valuation function is defined now relative to the variable assignment. And while this doesn't change how we define closed atomic well-formed formulas, it does give us a procedure for defining the truth value of open well-formed formulas. So let's kind of generally talk through an example, and then we'll look at a specific example. So the general idea behind defining the valuation function relative to the variable assignment is now we can define the truth value of well-formed formulas. We have a way of specifying whether or not the truth value of these formulas with free variables are true or false. So let's take the well-formed formula IXX, where I is the truth-place predicate, X is identical to X. We can specify the conditions under which this formula is true. We say that IXX is true relative to, again, the model here and relative to the variable assignment, if and only if the items that the variable assignment assigns to X are in the interpretation of I. That is, remember the variable assignment G is going to take the variable X and it is going to identify an item in the domain and say that this X refers to, let's say, Liz. And so the formula IXX will be true if and only if the variable assignment GX and GX is in the interpretation of I. To put this again, X is identical to X is true relative to the model and the variable assignment if and only if this ordered pair consisting of the variable assignment GX and GX is in the interpretation of I. And to put it even more straightforwardly, if the objects picked out by the variable assignment are identical to each other, then X is identical to X is true. So we have a way of determining the truth value of formulas that have free variables. Let's look at a more specific example. Let's say we have this formula CX, or X is a cat. The new valuation function is supposed to allow us to determine the truth value of this. And we have a way of determining the truth value of this formula relative to the model and the variable assignment. So we say that this formula CX is true if and only if GX, that is the variable assignment G, that takes the variable X, assigns X to an item in the interpretation of C, that is the interpretation of the cats. To put it more straightforwardly, this formula Cx is true relative to a model and a variable assignment G if and only if Gx, the item picked out by Gx, is in the interpretation of C. So let's just say that we have our variable assignment G and it takes as an input X, and this X picks out this particular cat right here. And this cat, since it is a cat, is in the extension or the interpretation of cats. So Cx would be true because the item picked out by Gx would be found in the interpretation of cats here. So all this is to show that we have a way of taking open well-formed formulas and determining its truth value. Now, if Gx did not pick out this cat, it picked out, let's say, I don't know, this little pebble right here, then Cx would be false because the item that X refers to is not in the interpretation of cats. So what we've done is specified two different valuation rules, one for closed atomic well-formed formulas and another for open well-formed formulas. But this doesn't really solve the whole issue because having these two different rules doesn't give us a valuation function that addresses formulas with both names and variables. So while it works for formulas like PA, LAB, PX, LXX, that is formulas that are closed and consist only of names, or formulas that are open and consist only of variables, it doesn't work for formulas that contain a combination, LAX, LXA. So the valuation rule here is still undefined, and we really like to fix this. What we would like is the valuation function to take either an open or closed formula with or without any kind of combination of variables or names, and to tell us whether it's true or false relative to the model and the variable assignment. So let's solve this problem. So to solve this problem, we're going to need to do two things. The first is to define the notion of a term, and this notion of a term is just going to be a concept that includes both names and variables. And then we'll define the notion of a denotation of the term that specifies the items in the domain that the term picks out. This is pretty straightforward, but let's kind of walk through it just so we're clear about it. So first, just the definition of a term. We'll say use T to indicate term. And so an RL term, a predicate logic term, is any name or variable in predicate logic. So for example, since X is a variable, it's going to be a term, because again, a term is any name or variable in predicate logic. Since Y is a variable, it's also a term. B is a name, it's also a term. D is a name, it's also a term. So pretty straightforward. A term is just any name or variable in the language of predicate logic. Now that we've defined the notion of a term, let's introduce some notation for the denotation of a term, and then we'll go ahead and define this notion of a denotation of a term. So let's let the expression square bracket T sub M sub G read the denotation of a term relative to a model M and a variable assignment G. So we're going to use these square brackets right here to indicate that we're taking the denotation of a particular term. And we're going to do this relative to a model, which is a domain and an interpretation, and a variable assignment. Now that we have this notation, let's look at what a denotation of a term is. That is, what this expression is standing for. So again, let's let M be a model, G be a variable assignment, and T be a term, which is again a name or a variable. So we're going to say the denotation of T relative to the model and the variable assignment, that is this square bracket T sub M sub G, is, and so now we're going to define it, it's the interpretation of T if T is a name, or it's the variable assignment of T if T is a variable. So in other words, if T is a name, let's say the name is A, then all the denotation of T, that is the denotation of A, is simply the interpretation of A. And the interpretation of A is always some object in the domain. And let's say A refers to the number 1. The denotation of a term T is the variable assignment t if t is a variable. So let's say that t is x, that is some variable. And we want to take the denotation of x, and this is defined as the variable assignment of x. And again, the variable assignment of a variable just takes the referent of that variable. And let's say x refers to 3. So all the denotation of a term is a way of picking out the referent of the item. So if it's a name, it refers to an object in the domain, and if it's a variable, it is some item in the domain. In the case of the names, it's picked out by the interpretation function, and in the case of variables, it's picked out by the variable assignment. It's helpful to look at some examples of a denotation of a term, so let's just kind of develop a model to do this. Let's say we have a model, and the model consists of a domain, and the domain consists of 3 numbers, 1, 2, and 3. We also have an interpretation function, and that interpretation function, we're just going to define it relative to the names, not any predicates. So the interpretation of A refers to 1, B refers to 2, C refers to 3. In addition, we have a variable assignment that takes all of our variables and assigns an item in the domain. So we have gx, that is a variable assignment g that takes x and assigns it an item from the domain, in this case 1. We have the variable assignment g, it takes the variable y and assigns it 2. And then last we have the variable assignment gz, and gz takes z and assigns it an item from the domain, and it's assigning it 1. Now that we have this model, which is the domain interpretation function, and we have this variable assignment, we can look at some examples of a denotation of a term. So in the first example, we have the denotation of x. And remember, the denotation of x is simply the variable assignment of x. And in order to determine the variable assignment of x, we simply look at the variable assignment up here, and we see that gx picks out the item 1. Here we have the denotation of a, and this is determined by the interpretation of a, and we consult our interpretation function up here, and it says it picks out the item 1. Next, we have the denotation of z. We say, okay, this is picked out by the variable assignment of z, and we identify it right here, gz, and this again refers to number 1. And then we have the denotation of b. Since b is a name, we look at the interpretation of b, and that's found up here. And we see, oh, here's a mistake right here. It does not pick out 1, it actually picks out 2. So the idea is pretty simple. The denotation of a term will pick out the variable assignment of the term if the term is a variable, and it will pick out the interpretation of a name if the term is a name. Now that we have this notion of a denotation of a term, we also have a term, and we can solve our issue where we had these 2 valuation functions, and we can merge them into a single valuation rule for atomic well-formed formulas. So here's the definition. Suppose we have a term t, and again, t is just since t is a term, it can be a name or variable. We also have p, which is an n-place predicate. Then we have the n-place predicate followed by n terms, and this is an atomic well-formed formulas. And since it's followed by n terms, these terms can be variables or names. We can specify that this formula is true relative to the model and the variable assignment if and only if the n-tuple that consists of the denotation of the terms is in the interpretation of the n-place predicate. So one more time. So we have a term t, an n-place predicate p, and then we have a formula that consists of the combination of those, and we say it's an atomic well-formed formula. We can say that this formula is true provided the reference of those terms, that is the ordered pair, ordered triple, or ordered n-tuple, is in the extension of the predicate. And if it's not, that is, this ordered n-tuple is not in the extension, then we would say that this particular formula, the n-place predicate p followed by n terms, is false. Let's look at an example now. Let's take LAX, an atomic well-formed formula, and we'll notice something about this atomic well-formed formula. It has a name A and a variable X. And we can say that this formula or this sentence stands for Al loves X. So we'll say that this formula is true if and only if the ordered pair that consists of the denotation of A and the denotation of X is in the interpretation or the extension of this loving relation. Again, the formula is true relative to the model and the variable assignment if the ordered pair that consists of the denotation of A, that is the referent of the name A, and the denotation of the variable X, that is its referent, the object it picks out, is in the interpretation of L. Put more simply, L loves X is true provided relative to this model and the variable assignment, the ordered pair, which consists of one item, which is L, and the other, which is the object in the domain that's picked out by X, is in the interpretation or extension of this two-place predicate X loves Y. So going back to our two rules, remember we had these two rules, a valuation function that's defined for names and one's for variables. Our new valuation function defines it over terms, and these terms can be either the names or the variables, and it has a way of combining the two together that takes into account both formulas with names and formulas with variables, as well as a formula that has a combination of those two, that is a combination of names and variables. So what we have now is a solution for our original problem, and that problem was that while the valuation function was defined for closed atomic formulas like PA, PB, RAB, it wasn't defined for open atomic formulas like PX, PY, RXY. Taking the valuation function and defining it not only relative to the model, but also to variable assignments allows us to define truth values for these particular formulas. But this only addresses one of the problems that I mentioned at the start of the video. The other problem is taking the truth values of quantified formulas and unpacking their truth conditions using names. So I'm going to go ahead and stop here, but I'll pick up this second problem in part 2 of this video on predicate logic semantics with variable assignments. If you have any questions or concerns, feel free to leave them down in the comments below, and I'm happy to respond to anything that you like further clarification on.